Let's embark on a journey to understand limits in calculus. Limits form the bedrock upon which the magnificent structures of derivatives and integrals are built. This is approaching without reaching, the foundation of derivatives and integrals. So, what exactly is a limit? In simple terms, a limit describes the behavior of a function as the input approaches a specific value, without necessarily reaching that value. Think of it as getting infinitely close. Here's the mathematical notation for a limit. Limit of f of x as x approaches a equals L. This is read as x gets arbitrarily close to a, f of x gets arbitrarily close to L. Let's develop some visual intuition. Imagine a graph where as x approaches the value from both sides, the function values get closer and closer to L. Notice that the function doesn't even need to be defined at x equals a for the limit to exist. The limit is all about the trend, not the actual value at that specific point. Now let's talk about one-sided limits. Sometimes we need to consider approaching a value from only one direction. On the left-hand side, we have approaching from the left side of a, where x values are less than a. On the right-hand side, we have approaching from the right side of a, where x values are greater than a. This is essential for functions that behave differently depending on the direction of approach. So, when exactly does a limit exist? Well, a limit exists if and only if both one-sided limits exist and are equal to the same value, L. In mathematical notation, this means that the limit of f of x as x approaches a from the left equals the limit of f of x as x approaches a from the right, and both are equal to L. Let's explore some common types of limits. There are two major types of limits: finite limits and infinite limits. For finite limits, the function approaches a specific number, L, and this is the most common type in calculus. For infinite limits, the function grows without bound. This often occurs at vertical asymptotes. Let's compute some simple limits. One of the easiest ways to compute a limit is by direct substitution. Here is an example. To find the limit of 2x plus 1 as x approaches 3, substitute x equals 3. This gives us 2 times 3 plus 1, which equals 7. Now let's consider another example. To find the limit of x squared minus 4x plus 5 as x approaches 2, substitute x equals 2. This gives us 2 squared minus 4 times 2 plus 5, which equals 4 minus 8 plus 5, which equals 1. Indeterminate forms. These are cases where direct substitution fails. Common indeterminate forms include 0 over 0, infinity over infinity, and 0 times infinity. These forms don't immediately tell us the value of the limit, and they require special techniques like factoring, rationalization, or L'Hopital's rule to evaluate the limit. Now let's see how limits are connected to derivatives. The derivative is defined as a limit. Here is the mathematical form. F prime of x equals limit of f of x plus h minus f of x all divided by h as h approaches 0. This connects the concept of instantaneous rate of change to our understanding of limits. Finally, let's explore the link between limits and integrals. Integrals are also defined using limits. Consider the definite integral of f of x from a to b. It is equal to the limit as n approaches infinity of the sum of f of x sub I times delta x. Therefore, limits are the foundation of all calculus concepts. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.